All right, let's get going on this last example for this set. So we're going to do a higher order problem, y double prime minus 3y prime plus 2y is equal to e to the minus 4t, with y of 0 equals 1 and y prime of 0 equals 5. And if we were solving this like the old way, we would do this, first we have a constant coefficient problem, and then we have a like undetermined coefficients problem. But we're going to solve it all together at once using Laplace transforms. And you'll be able to see that this is the same type of answer with like exponentials as we would expect from last chunk of videos. So I'm going to start out by taking Laplace of both sides. So my L of y double prime minus 3y prime plus 2y is going to be by linearity L of y double prime minus 3L of y prime plus 2L of y. And then I'm going to have to use my derivative rule. So for second derivative, I start with s squared and I multiply by capital Y. I subtract s and use my first initial condition. I keep subtracting until I run out of powers of s, which happens to be just one extra. Then for y prime, it's first derivative, so I start with s times y. Then I go down to no powers s, and the first initial condition, y is 0. And then for Laplace of y, oops, gotta add it at least. Then for Laplace of y, that just turns into capital Y. And then I'm going to want to go ahead and plug in my initial conditions so that they are a little easier to work with. So that's s squared y minus s times y of 0 was 1 minus y prime of 0 was 5. I'm going to distribute that minus 3 through. I'm going to note that when I multiply minus 3 times minus y of 0, it becomes plus 3. It's really easy to make that kind of mistake. I'm sure you've done it at some point in your life, maybe very recently in class. What's important is that in these Laplace transform problems, messing that up can be the difference between like a very easy fraction decomposition and something that becomes a huge mess later. So really be careful in this step. So I've got minus 3sy, and then plus 3y of 0. The y of 0 was just 1, so I just have plus 3. And then I've got that plus 2y. And then I'd like to eventually solve for capital Y, so I'm going to go ahead and group everything that's multiplied by capital Y. I've got that s squared minus 3s and plus 2. And then everything else I can go ahead and leave outside. I've got minus s minus 5 plus 3. Just my extra terms. And at this point I think I've simplified Laplace of the left side as much as possible. So I'm going to go ahead and do Laplace of the right side, L of e to minus 4t. And this we're just going to use that L of e to at equals 1 over s minus a. For us, a is minus 4. So we're just going to get 1 over s plus 4. That's minus 4. Then setting both sides equal, we have s squared minus 3s plus 2y minus s minus 5 plus 3 is equal to 1 over s plus 4. Or solving for y, we're going to get that y is equal to minus 5 plus 3 is minus 2. I guess I should simplify that at some point, and that point is now. So then when I move that over to the other side, I'm going to get s plus 2. Just I'm adding s and 2 over here. And then everything gets divided by the thing that multiplies y. So that's over s squared minus 3s plus 2 plus 1 over s plus 4 times s squared minus 3s plus 2. I'm not going to make you sit through watching me solve another partial fraction decomposition problem, but that's how we're going to solve this. If you want some practice, I guess you could do it on your own real quick, but I'm just going to go ahead and write out the result of the decomposition. So we're going to want to turn this into something that is s plus 4 type terms. And then when we factor that s squared minus 3s plus 2, that's made up of s minus 3 type terms. No, sorry. That's made up of s minus 2 type terms and s minus 1 type terms. And if you set up the problem just like we did in the last example, you end up getting the coefficients that there's minus 16 over 5 for this one, 25 over 6 for this one, and 1 over 30 for this one. So hopefully from the size of those numbers you can tell it wasn't exactly a pleasant process to get there, but it is something that I know you're capable of doing. I'm going to move to the last slide to just do the final step of undoing Laplace. Go ahead and pause if you need some more time here. But now I'm going to need L inverse of that capital Y, which is L inverse of 16 over 5 over s plus 4, plus 25 over 6 over s minus 2, plus 1 over 30 over s minus 1. And we're going to be doing this by linearity. So we're going to pull out that 16 over 5, think about L inverse of 1 over s plus 4. Pull out that 25 over 6, think about L inverse of 1 over s minus 2. And pull out 1 over 30 to think about L inverse of 1 over s minus 1. What's nice is that these are all those exponential ones where you don't need anything in the numerator, so we don't have any of that clever balancing to do. But this is when you would check to make sure that you don't have some factorial that needs to be up top, or like the k in a sine function. Then plus 4 means a is minus 4, minus minus gives me plus. Minus 2 means a is 2, and minus 1 means a is 1. So then just taking these inverses, I've got 16 over 5 e to minus 4t, plus 25 over 6 e to 2t, and 1 over 30 e to t. And that's the solution. I'm going to pause for a second for people to catch up writing, and then I just want to talk about the types of terms we're seeing here. I'll actually just go ahead and rewrite it here. So this is the problem we were solving, and if you think back to the last exam worth of material, we would have guessed the yp is something like e to minus 4t for undetermined coefficients. So that's this term. And then plugging in our constant coefficient process would eventually lead to solving this equation, which factors, same way breaking up this denominator did, we're creating that same term again, into m minus 2 times m minus 1, so we'd get m equals 2 and 1. So that gives us our e to 2t and e to t type terms. That's what's happening here. And then those numbers, the one on e to minus 4t would come from undetermined coefficients, but this 25 over 6 and 1 over 30 would come out of an initial value problem, solving for C1, C2. So this is addressing the same type of problem, but in a different way. Everyone has their preferences for which one they like more. Personally, I just like partial fraction decomposition more than most anything else, so I would probably still take the old approach. But a lot of people like Laplace because it's 4 steps, same 4 steps, just go through it and you'll get to the right answer. So we'll keep working with even more complicated differential equations in future videos. But that's it for now, so I'll see you next time.